students. I was talking about the spatial compaction techniques which we use to obtain the better quality of our product, and it is mainly due to the enhanced density and the microstructure that we obtain in our the finished product. So in my previous lecture, I gave you some information about the isostatic pressing. So this isostatic pressing means the pressure is applied from all the directions, and this compaction is taking place in a flexible mold. And the pressure had this pressure was applied with the help of some water, oil, or with the help of some gas. So basically, there are two types of isostatic pressing. One is the cold isostatic pressing, and other is the hot isostatic pressing. And as the name suggests, this cold isostatic pressing, so this type of pressing or compaction is taking place at the room temperature, and pressure is applied with the help of water and oil. And this compaction pressure is usually less than 350 megapascal. And what is the advantage? Advantage is that you get more uniform density as compared to the conventional powder metallurgy process, powder metallurgy compaction process. So in this figure, again, I am repeating that this is a process in which this is a mold cavity, and there is a center solid core pin, and this cavity or this mold is made up of rubber flexible mold, and you have filled your powder, and from this opening you are applying the hydraulic pressure with the help of this hydraulic oil or water, and then it causes the compaction from all these sides, and then you have a uniform density in your finished product. Okay. And this is basically a relatively cheaper process as compared to the hot compaction technique, and it gives shorter production cycle time. So this is very favorable in the industries in order to get the required strength and uniform density in your product. Then after this, we have hot isostatic pressing technique, and basically this process is carried out at very high temperature, say up to 1200 degrees centigrade, and the benefit is that you don't require such pressure, and the pressure is usually capped to a level of 300 MPa. But however, in some case of very high strength powder material, this can reaches up to 300 MPa. Okay. And the pressure is applied with the help of argon or helium gas, which is used as a compressed medium. And this mold cavity here, in this case, this mold cavity, earlier it was of rubber mold, but now the rubber cannot sustain such high temperature, therefore you are replacing it with the help of a very thin sheet metal. And these powder metallurgy parts, which are made by the hot isostatic pressing, they are characterized by high density, and porosity is nearly to zero. We cannot say that it is zero, but you can achieve density up to 98%, 99% density, and there is a proper interparticle bonding, and the result is that you have a good mechanical strength as compared to the cold isostatic press part. So this is a very short description about the hot isostatic pressing and cold isostatic pressing. And I have also included some videos in my Google Classroom. So I request you all to see those videos, and then you will have a better idea that what is that process, how to carry out this process in a controlled environment, and what are the things which are associated with this process, and how you should take care of the product quality and the safety of the operator. And all such process require very sophisticated tooling. Press will be of some different type, and your die will be of very good quality and high temperature resistant material and high strength material. So this is a very brief discussion about hot isostatic pressing. Now the next process is combined pressing and sintering. So combined pressing and sintering, yesterday one student asked me, sir, that why we are not carrying out this compaction at high temperature. So basically, here in this case, this is your answer, which is your hot pressing, and it is very similar to your conventional powder metallurgy uniaxial pressing, except that the heat is applied to the mold and die cavity during the compaction. So this is, as you can see from this figure, that this is a press, which is a schematic diagram, and the centrally that over top is the upper portion is the upper punch, and then bottom is here. You have a bottom punch, and this punching is taking place in this confined area where you have a powder filled, and the die cavity is surrounding with the help of a resistive heating element, and this whole compaction zone is encapsulated with the help of a ceramic hot tube, which prevents the you can say the dissipation of the heat from the heating zone, and then you get the good densification, and you get a hard and strong dimensionally accurate product. And this type of process is usually applied for the fabrication of sintered carbide products such as the graphite molds. And the benefit is that you require less pressure as compared to the conventional cold pressing. Okay, so this is the hot pressing technique, and just the difference is that you are applying pressure and as well as the temperature simultaneously, and which will result in the improved density of the product. After this, we have another advanced process. This is basically a relatively advanced technique, and it is known as spark plasma sintering process, and it is also known as pulse electric current sintering, PECS, and sometimes it is also known as field assisted sintering technology. And this process employs a pulse DC current, which is used to heat up the electrically conductive tool. So you have basically our upper punch and the lower punch, and this whole process is carrying on in a vacuum chamber. The graphite, the die is made up of the graphite, and then from the upper punch and to the lower punch, you are applying a DC voltage, very less DC voltage of 5 to 10 volt, and however the pulse frequency, you are applying this pulse DC current, and the frequency is very high as compared to the conventional frequency, which is your 50 to 60 hertz. So here the pulse frequency is in the range of 30 to 40 kilohertz, and it results in the electrical heating by the Joule heating effect, and you get a very high heating and cooling rate. So as you can see from here, the data given is here that you can achieve even 1000 Kelvin per minute. So this is the heating rate, and as you can see from the figure A and B, a comparative difference between the microstructure obtained in a hot isostatic pressing and a spark plasma sintered product. So you can see there is a uniform microstructure in the spark plasma sintered part, and very less density as compared to the hot isostatic pressing technique. Now the question arises that this is you can say this is a heating process. So where is your spark? Where is your plasma? So basically, when you are applying the electric current DC voltage, so what happens that the pores which have occurred between, which have formed between the interparticle space, this is getting electrically charged. So this is charged up, and you see a sort of arcing there, and at the surface of the particle there is a glowing plasma, which breaks up the thin film already formed. Sometimes the film forms during the you can say the storing. The film of oxide layer can also be formed on the surface of the powder particle. So during the sintering process, this oxide film poses a problem during the sintering of the part. So this electrical current, this high frequency and low voltage current it helps in breaking that oxide film, and at the surface of the individual particle you see a sort of plasma, some charge glowing on the surface, which improves the material transportation during the neck formation. So we have already seen that in the sintering process what happens that there is a diffusion of the atom takes place, and then slowly the neck formation takes place. So due to this arcing and plasma, the material is localized on the surface, and you achieve a good bonding among the particles. So this is basically your spark plasma sintering process, and this is relatively a process which gives you shorter production time, and the sintering time is not more than 10 minutes. In most of the parts, 10 to 15 minutes is the maximum size, the maximum time period, while in case of conventional sintering process we have seen that the time goes up to 1 hour or 2 hours depending upon the part size. So, if you like the video, then please subscribe to my channel, share it with your friends, and don't forget to hit the bell icon for the latest updates. Thanks for watching my videos.